Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about ICE Thermal Energy Storage or ITES. So let's dive deep into it. So what exactly is the idea? Well, idea is very simple. We can store energy in the format of water ice. Now here's the ice is a common thing. It happens in everything. Like CO2 can become dry ice. So we are talking about something where we convert ice water from liquid to solid phase. Now, why do we want to do that? Well, here's the deal. Water is very uniquely suited for that because it has huge energy capacity per liter of water. Meaning if you have 1 ton of water, around 1000 liter or 1 kiloliter, you are looking at 185 kilowatt hour energy. And that's going from 0 degree to 0 degree Celsius. It's like, wait, then where did energy come? Fusion energy, meaning the energy that is required to bond all the basically free floating molecules into one solid ice block. Not one physically huge molecule, it's just that together. Like that takes fusion energy, insanely large amount of energy. So you do not even need to heat up the water. It will take bonkers amount of energy, and you will that's why whenever you are freezing water, the temperature gets stuck at 0 degrees Celsius. Now you're taking all the energy away. To super cool ice, it's very difficult because ice is almost like an insulator. So just at 0 degrees Celsius, you can get 0 degree water in and water out, or a coolant in and out, while getting energy out of it because of that ice melting ability. Lot of energy is there in that phase shift. That's our key sweet spot. Now, we can use energy for cooling. Now, this is one thing that we have to change how we are perceiving right now. Right now, we are like electricity, save electricity. That's not necessary, nor it's wise for everything. Now, this is coming from the old days where we were like, okay, we have fuels, we pump fuel into the machinery give us energy, be it coal, be it natural gas, be it whatever, and that's how you get used to energy. So we are always energy focused, but now we are not in that sweet spot, so to say. However, we have intermittent power. We have abundant power, but it's intermittent, meaning it has its own flow of it. So we could try to store it. That's a good thing, but it's not necessarily the only tool. We have other options. For example, what the hell you're going to do with your basic electricity? For example, there was a recent issue with power grid in my area, local area, and the power went out at night. Now here's the deal. How did I know? I woke up from the sleep because again, this upper floor gets very hot. Around the wall reaches around 30 plus degrees Celsius, and if AC is running, okay, it's livable. But the moment power goes away at night, the building's heat starts to roast me alive again. So that's how I woke up, and it's like, yeah, it's uncomfortable. Now here's the deal. At that point, what do I want? Do I want electricity or do I want cooling? Now, like, if I get electricity, what will I do? I will use that to run AC. So core point is, know what you are doing. For example, for many industry, what the hell you gonna use your energy for? Are you gonna spend it for cooling, or you gonna, like, spend it for heating? If you are doing it for heating, directly store the heat. It's much more effective. Again, for cooling, directly make ice is far more effective rather than having giant battery banks storing that energy, then running compressor when you need to. Unwise. Store energy directly in the format that you need to. So that's the core point. And because of the density, like even 1 ton, which is 1 kiloliter, it's huge capacity, meaning even a freezer, chest freezers and all that can store a lot. A big box can store more than enough energy capacity in a floor basement that it can handle a skyscraper. And yes, that's a real life. So, and these sort of units that can handle small districts. So you're talking about some serious capacity. Everyone's like, how we can store megawatts of energy? But if you don't, what if what you need, what is your primary requirement? Oh, your primary requirement is air conditioning. How about you store ice? It's far more effective. So that's the whole point. That's the idea. Store energy in the format that you need to. So what's the science behind it? Well, science is, there are few things in flux that changes the equation. First is heat pump. Whatever you are dealing with, like AC is here, refrigerator, or whatever have you, they all are heat pumps. So whenever you're talking about vapor compression system, it's a heat pump. It takes heat from one point, dumps it into another point. So a cold reservoir is created and hot reservoir is created. However, what is the efficiency of it? For the efficiency of it, we use COP, coefficient of performance, meaning it's a multiple of the compressor output. So for example, in my case, the compressor is around 1.5 kilowatt. Does not mean it has 1.5 kilowatt of cooling. That would be horrible if it has that. You've seen the small Peltier module? Yeah, that's why we do not use it for refrigeration. That has 0.5 COP, meaning if it's 1 kilowatt, you will be lucky to get 500 watts of cooling out of it. And yes, that means as a heating element, it's 1500 watts of heating element. And in terms of refrigeration, we hope anytime you see tons, BTU, those are assumed unit multiplied by a COP. So electro energy, as in like 1.5 kilowatts multiplied by 2, multiplied by 3, whatever have you. So this is a very simple graph to understand these things. Differential makes everything worse. For example, if you are in a scenario where the outside temperature is hot, let's say India, 45 degrees Celsius hot, compressor is working its ass off. It's having very hard time condensing the refrigerant on the other end, basically having hard time dumping energy in that. And you are trying to set your indoor temperature to 20 degrees Celsius. That's a refrigerator. Now here's the deal. What happens? Same 20 degrees Celsius, but the outdoor temperature changes. Let's say it goes from 45 degrees Celsius, where you are barely getting 2.5 COP, multiple, that's a multiple of your kilowatt of the compressor. So you will go from 2.5 to 3.2. You are almost getting 1 extra kilowatt of heat energy simply because the outside temperature changed. And that's the core thing that you must understand. Differential, the worse your differential you have, the worse your problem will be. So you always want your differential to be as low as possible. You want inside. That's why many new ACs have the saying that keep it to 25 or 26 degrees Celsius to save energy. The lower the differential, the more energy, more heat can be pumped without consuming a lot of electrical energy. For example, if you reduce the differential to, let's say, 30 degrees, at that point it's just a heating element. But let's say 22 degrees Celsius, again COP improves from 3.2 to 3.4. And given the fact that we spend a lot of money, going from 3.2 to 3.4 is huge. So this is the core essence of everything. The bigger the differential that your compressor has to work against, harder its job would be, more energy is going to consume and less cooling is going to do. For us, it translates to a scenario where from 12 noon to around, let's say 2 p.m, it's so hot that our AC could be like, compressor going, cooling is like, it does not cool. Same AC, same house, same day, at evening time, I turn it on, half hour is like, chill bro, I got this. How the heck? Again, outside temperature. Outside temperature affects this puppy, that affects the compressor's ability to dump heat. And that's why the ton rating, the BTU rating is lol. Unless company gives you graph like this, you do not know what is the cooling power. And again, humidity also has to be there, but that became too complicated. So what's the essence of making ice? Well, day and night differential is huge. For example, this is India's Ahmedabad, a very big metropolitan city, and you can see it got a bit hot, a bit excited, 45 degrees Celsius from that 12 zone, and at night it was as low as 31 degrees Celsius. Now, if you're running the AC at 31 degrees Celsius, if I give you 10 units of electricity, how much ice you can make in this spot versus in this spot? Exactly. In the cooler spot, you will make more ice. That's why same electricity was consumed exactly the same amount. Compressor exactly the same. Refrigerant exactly the same. Everything exactly the same. But because of the lower differential, as in the lower work that your compressor has to do, it got more work done for less energy it consumed. It's better for you. It's better for environment. It's better for your bank balance. That's the biggest advantage we have. That's why we want to load shift. We are still doing the same amount of cooling, but we are shifting it. Where compressor is like, I got this, I got this. You do not fight against your compressor. Please pump heat in 51 degrees Celsius. No, you're like, bro, chill, I got you, I got you. You only turn on the moment sun goes below the horizon. The moment sun goes below the horizon, Earth starts to radiate heat into the space. It starts to cool down. When is the coldest? Well, just before the sunrise, because it's continuously dumping the heat, and you can notice there is a slide from the moment sun goes below the horizon, Earth starts to cool down. Cool, 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 cool. Again, sun comes up, it heats. Again, cool, 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 cool. So horizon. The moment sun goes below the horizon, you turn on your condenser, so to say. It's like, bro, go. Now it's like, I got this. And the longer hours it works, the Earth is making its job much and much easier. So day and night differential is very high. How high? In numbers, you are looking at 15 degrees Celsius. So you can go from 45 degrees Celsius to almost 35 degrees Celsius, or maybe even 30. Again, 45 to 30. You see how much COP would be improved directly. So that's why we want to do that. And you may be like, that's like 3.2 to 3.5. Yeah, it's huge. Realistically, it's huge. Think about like a city. Think about hundreds of AC doing that. That's huge. So someplace. And here's another thing, which is awkward in India, but for very comfortable for Western people. It's like nighttime and daytime pricing are different. So almost every place, be it India, be it China, be it Russia, be it wherever, commercial places specifically, they have a cheaper power rate during some times of the day. Meaning, if there are times in the day where you can make a lot of energy to store, it's economically viable to do so. For example, in Western countries, at night time, they want you to consume electricity because it's super easy. They do not want to consume everybody at the peak time. Basically, here, they do not want everybody to consume, like what happens in France in 2020 or 2022, where they had all the rivers dry out and everybody was running their compressors all out. The peak load was so brutal. It was like the grid almost reached a point where it's like, whoa, 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 we are about to cook off. So you do not want that. As a country, you do not want that. As a grid operator, you do not want that. As customer, you do not want that. You want everybody load to be spread out. How do you do that? You offset it. You're like, hey, what if I charge my buffers at the night and then you coast during the peak hour? That's the whole point. And cheaper rate in India is weird because we're going to get energy savings in this slot, hottest time. Now, like, why? India went way too much in solar. So we have a lot of power. So country is like, hey, what if you load shift during day? So I think commercial people will be able to utilize it very effectively. And I will share one way how they can utilize that in daytime in India. So that's the science behind it. There are a few variables that are in play. First, outdoor temperature directly affects how much cooling you are getting, even though compressor, refrigerant, and everything remains the same. And there is a cost advantage. Depending on certain scenarios, depending on your location, you could be in a scenario where it's like if you are running your load at night, same amount of units, as in like 100 units of energy, would be cheaper to buy if you are buying it compared to peak time. So all these things combined, given the fact that India has a differential of 15 degrees Celsius, there is a lot of potential here of coupling efficiency. You want to improve what we call coupling efficiency. Same amount of energy will be consumed, but the work done would be more. So that's the science behind it. So let's look at real world example. Chicago cooling system. Somebody went too serious with this and you're like, what if we cool the city? So the idea is that you have skyscrapers. Now skyscrapers have a lot of people. So as in like our body is bare minimum 100 watt of heating element. It could go to 200 watts and electrical load and all that. So it becomes a giant heating element. So how did we used to solve it in the past? You put bonkers amount of chiller in the basement. Like whole basement would be filled with chillers. And then you're going to have giant water pipes going to the rooftop. And you're going to have giant air handlers that are dumping the heat, water cooling tower basically. So upper floors will literally look like an industrial section. Bottom basement will look like an industrial section. And then you're going to have people comfortably living there. Now, here's the deal. You do understand that this starts to get too crazy. And again, that's another reason why people are not interested in making super tall buildings. Like, how would you cool it? Like in some buildings, it's so bad that they have like few sections in between, not in the basement, not in the top, like in between where they are dealing with the refrigeration requirement on there itself. It was like too cumbersome. So what basically Chicago did is very simple, where it's like, okay, what if we give you a heat exchanger in your basically basement, smaller size of course, because it's not compressor, it's just a heat exchanger, and we give you 0 degrees Celsius water, and then we take like 15 degrees Celsius water out of it. That's a lot of what you call delta. And again, water is very good at conducting heat. Basically, if you're thinking 0 degree and 15 degree, that's not enough margin. Yeah, try doing that with water. It's a lot of capacity, lot of oomph that you can dump into it. So you have your energy transfer station, which they call it, and then that controls your what we call air handling units. Air handling units are just like your AC, normal AC that you have, and instead of refrigerant running through it, it runs water through it. And yes, it also dehumidifies because the water is so cold. Like put a cold water in your glass, you will see water condensating around. Yes, it does condensate. Not as quickly as a basically refrigerant based system, because the refrigerant can go minus 18 degrees Celsius, but still does work. So due to that high screech, the cooling load is very high and the space is at a premium. They can't just build things to handle it. Like you cannot just like, okay, top 10 floors is just a giant chimney for air cooling. Yeah, it becomes impractical. And multiple water tanks are used. So this is the map, and there are multiple tanks like P2, P1, P4, P5, P6. So they have a lot of production sites, and these sites are huge water tanks, nothing fancier than that. Just huge water tanks. And yes, this is a building. And yes, this is another building where 2 floors just for water tanks. Nothing more than that. Water tank. Huge water tank. And I want to figure out who built this building, because I'm reasonably sure water on that size would be heavy AF. And I'm pretty sure I want to figure out who built the pylons for it. So giant water tanks. So what they do? Nothing during daytime. They do not. They start at the night time, freeze the whole water block into ice, and during the daytime where compressors are like working their ass off and dying, they're like, no problem. We take the water from the buildings, we dump it through our ice block, then ice block sends a cool water out, and voila, now you have a cooling, and you do not have to run your compressor on the peak time. How big of a difference that would make? Well, here's the deal. They have 5 plants and all that, and it's making every building who's in the system, if I'm not mistaken, they have around 100 plus building in that system. They're looking about 30 megawatt of peak saving. Let that sink in. 30 megawatt. You take the power drop, remove 30 megawatts from the top. That is shut up, take money. And they will be expanded. Now be mindful, this is not unique to basically Chicago, but Chicago has the biggest ICE unit. Other countries like Dubai, they are also building something similar like this, but they do not have ICE. They are utilizing the what we call benefit of scale. So if you want to do this, even in daytime, it still would be more efficiency, more beneficial to do this compared to like directly running everybody's smaller units. Because again, when you have large units, you can optimize it. You can have multiple systems, multiple redundancy, optimization, maintenance, all of that. So overall, the benefit of industrial scale is it works at peak efficiency. So, and again, if you have giant area dedicated for giant cooling fans, you can have huge fans. You can have like stuff that can manage it. Output would be awesome cooling power. So Dubai is doing that. They have not gone into ICE system. Last time I checked. Again, I do expect them to switch into it because again, differential for them could be as high as 20 degrees Celsius, meaning peak daytime and peak nighttime could be 20-degree differential. That's huge once they go into ICE. Singapore has started to do ICE. Hong Kong airport, they are also making giant ice block. This is a series. So this is a very optimistic way, very realistic way of optimizing heat load without frying your grid. And during daytime where every compressor is like, I'm working my ass off, they're like, bro, chill. Literally, chill. I got it. I literally got it. Don't worry about it. Nighttime. Think about it. 30 megawatt of every day you're like, your grid is like 30 megawatt less. And like, that does not matter. It's like, yeah, it matters. It's more than zero. It matters. It's efficient, it's optimistic. And again, they have learned a lot and they designed the system in such a way that if any one unit goes down, they can handle it. So Chicago cooling system, really good, really large scale and really going YOLO on ICE. Singapore is close behind. Hong Kong airport is third behind. And again, Dubai might jump into ICE and they're like, okay, why the heck we did not do this earlier? So this is large scale deployment of the same thing. Huge energy saving. And again, I'm talking about only the energy saving, the megawatt. Money-wise is bonkersly high. Why? Nighttime electricity is cheaper. So money-wise, they are saving lot of money. Exponentially more money because 30 megawatt at peak time, it's very expensive. 30 megawatt at off-peak, chill bro. Now, let's talk about small scale. Here's the deal. You can have small scale like this, like a small thing. Like you can just go and do it. You do not need to industrial level stuff. You can do a small scale also and you will get the same benefit because you have to understand when you are talking about ACs, like let's say this puppy, Blue Star inverter AC, that is 1.5 ton. What does that mean? That simply means if you had 1.5 ton of ice and you let it melt over 24 hours of time, 24, one whole day, the energy that it took to melt it was equivalent of that. So 1 ton AC simply means you need 1 ton of ice melting over 24 hours. So basically, if you want to convert it, how much water I need in order to phase change and be replacement, take tonnage multiplied by kiloliter. So if you have 4-ton system for a medium size house, multiply 4 by kiloliter, so that gives you 4,000 liter. Put a bit of buffer, let's say 5,000 liters or 5 kiloliters, and you're good, you're sorted. Now, you can also do another things. For example, a lot of people, in this example, I have linked the video down below. The gentleman is like, yeah, we are running it with solar, but here's it. If you try to do it that way, like your solar is giving you the most power, generally there's a very peak heating at that time also. So your compressor would be working very hard. It's a very easy and effective way of storing energy, much cheaper than having giant lithium-ion batteries. But what if at that time they did it very cleverly? It's like, what if we heat water at that time rather than basically you need to pull heat out of this, right? This is your cold reservoir. You want to pull heat out of it. Where do you dump it? That makes your life easier or hard. So you pull the heat out, you dump it into hot water. You make hot water. Again, you had to spend energy for it. So now you're getting it for free. You're just transferring heat from this to hot water. You get hot water. It's cost effective and utilize basically solar energy at peak time, whereas like rather than having giant battery, you're like, hey, very small battery, because our majority energy consumption is cooling. We're like, hey, ACs are just running as air handlers. You are just running liquid, small pump, and you are running from like air to basically liquid heat exchanger. Almost exactly what you have in your refrigerant based ACs. Instead of refrigerant is just water and fans are still running. not enough load. So you do not have to spend boatload of money on batteries. So this is a very effective way of taking off-peak power. So it's like, hey, what the hell are we gonna do? Like, you have so much power. It's like, hey, what about you store it into ice? What about you get hot water out of it also? Again, even if you are not doing hot water, it's still an effective system. So small scale is also there. However, be mindful, I'm more designs I'm saying the small scale, apparently it only makes sense to use plex pipes, not this. This is from ICE Energy company, and this gives me anxiety simply because these are copper pipes. They have designed it quite eloquently. Everything is awesome, but here's the ICE expands and contracts. So I do not expect these pipes to last very long. Meaning, of course, I do not expect it to like break apart and all that, but I do expect this to like fatigue very quickly because again, ICE expands and contraction. They must have some faith into that design, but more designs I'm saying, the more they are like, hey, let's just use plex tubing. Yes, it's less inefficient, less efficiency because again, conduction is not very good, but it's a closed loop system. It does not matter that much. So small scale also do. Like, you see, like it's quite small scale. You do not need giant tank. Again, giant tank, giant capacity. So this is a very awesome way of doing same tools, same products, just a little bit of space, and you're going to get amazing result. You can shave off peak or store off peak energy. Now let's talk about India. Now here's the deal. India is getting hot, and the good news about this technology, this is neither complex, neither magical. Like it's just a tank, a insulated water tank with plex tubing. Again, you can even do stainless tubing, but I still have doubts about, because again, metals are awesome unless they fatigue. And when you are talking about day and night, day and night, day and night, I do not expect them to last very long time. Again, you can design it very well, but it's like, now it starts to cost money. So plex tube, good. So it's nothing magical, nothing complex. It's a very simple system. What about coolant you run? You run generally water. Wouldn't that freeze? Generally, a little amount of antifreeze is added to it. Very small percentage, because again, water is awesome at conducting. So you do not want to replace, let's say, water with something else. You may think oil would work. It will work quite phenomenally. It's just you have to pump a lot of oil to get the same amount of cooling, because again, oil does not have enough thermal capacity. So glycols have been used because again, refrigerant line does get colder. Refrigerant line, if you try to run it with water, it will not work out, because the moment it touches refrigerant could be as low as minus 18 degrees Celsius, or maybe even lower. Some designs like they are using propane as a refrigerant, those puppies can touch minus 40 degrees Celsius. So it can flash freeze. So even running at very high pump speed or salty water, yeah, it's not that great. So for that reason, glycol has been used. Propycol, there is a different mix that is not as toxic as glycol, that can be used, or oil in that regard can be used, because again, at that time you do want that capacity, so to say. So it's neither complex nor magical. That's very good. And India has very high differential. It actually makes it easier for us, where it's like, hey, daytime frying to 45 degrees Celsius, 46 degrees Celsius. So it gets very hot. And nighttime, actually, it's like, okay, we have majority of this area is plateau region, basically giant rocks. So it dumps heat quite effectively. So we can actually utilize that. And what kind of energy saving you are looking at? You are looking at 10% on a suboptimum system, to most optimistic scenario is 30%. Now be mindful, these numbers are from real world projects. It has been achieved. Now, like, that's not a lot. Here's the deal. Imagine on a country scale. That's shut up, take money. Be mindful. This number is greater than zero. This number is more convenience for you. Flat out, shut up, take money. That's why I talked about it, like 30 megawatt. People are like, oh, 30 megawatt is not huge. It's like, it's 30 megawatt above zero. Everybody is happy about it. So this is super awesome. Even at 10% energy saving, you're talking about India is getting so roasted that we are putting bonkers amount, like gigawatts of power just to cool our homes. If we can save 10% in that gigawatts of power, let's say 10 gigawatt, calculate 10% of that. Huge. That has cascading benefit to us. So it's a flat out doing that. Now, what about commercial sector? Again, right now, India's residential sector is not getting differential power bill. The law is just went into effect very recently, and right now it's only for commercial sector and industrial sector. So triple dipping is possible, meaning if you are a hotel or a hospital, which again comes into commercial and industrial section, you are dealing with again high tariff. You will have to deal with that tariff, meaning if you are consuming power during daytime, awesome energy saving, meaning your bill per unit consumed would be less. But at night, what will you do? Now here's the deal, you can do triple benefit. You can get hot water during that time, meaning if government says like from, let's say 11, not 11, in India it would be, again, state government has to give that law, and that has just come into effect. I did not find exact precise detail. So it's supposed to start from, let's just say 9 a.m. to, let's say, 5 p.m. In that time, your tariff would be, electrical tariff would be 10 to 30% less. Okay, awesome. So that time you heat water. You do not dump energy into hot air, because again, it's very difficult. Doable, but difficult. So you get hot water out of it. After that, your AC is like, you have giant chunk of ice, and you already paid very less power cost for it, because again, low tariffs. Then at night time, you still recharge the ice that melt, now utilizing high COP. So you can get three benefits. You're gonna enjoy a lot of high COP, you're gonna enjoy a lot of low tariff, and you're gonna get basically hot water as a byproduct. That way you can do triple dipping. Again, it will not work with every field, but it will work with residential sector. It will work with basically any place where you need hot water and you pay money for getting that hot water. That's like, shut up, do this. And again, this also solves our issue where it's like government is like, daytime free. It's like, what the hell I'm gonna do in daytime? It's like, hot water, I can do that in daytime. Again, residential will have not that much consumption. Again, washing machine requires hot water, and dishwasher is not that successful in India, so not that much demand. Hotels, because again, laundry, they consume water like there is no tomorrow. Hospital, sterilization and other stuff, they consume like there is no tomorrow. So for them, it's like, shut up, take money. But others, it's like, can be done, better than nothing, but very good technology for us. And it's really shocking to me that nobody has done it, and there is no patent lock and all that, unless like exact design may be patent locked, but not the core technology. This is a river base, like a lot of homeless people are going there to take care shelter in the sun, because again, it does get hot in India, like hot. So this was my presentation on ice as a thermal energy storage medium, and hopefully you guys have liked it, learned from it. In that case, please hit the like button, share it amongst your friends, that will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.